In the last video, we defined instantaneous velocity, and now we're going to go from there to define acceleration. Now, here's where things can be a little challenging, and if you find it a little hard to process, it's okay. The brain does some weird things for us. It turns out that the way our brains are set up, it has hardwired into it a very thorough model of physics that's designed to very quickly and very efficiently figure out whether, say, a rock might hit you. And it's very good at being able to figure out whether or not you should duck if it looks like a rock might hit you. It turns out that unfortunately this model of physics that is hardwired into our brains is incorrect. And so what you wind up having is what's called the misconception of the impetus. And this turns out to be a big, huge mess of ideas that are all balled together into one pile of goo. And a lot of what we're going to have to do in these videos is slowly tease out one piece after another that's all schmuzzled together into this misconception of the impetus. So that means that what you're going to be seeing has pretty good odds of running a little bit counter to your intuition on how things ought to work. And that's okay. All I can say is we've all been through this, and with practice, it gets better. So with that happy note out of the way, let's go ahead and define acceleration. So acceleration is defined to be, and again, it's the same limiting process we had before. It's defined to be the time rate of change of the velocity of an object. Now, some things to watch out for here is, for instance, the acceleration and the velocity can have different signs. And so how would we interpret that? So for instance, let's say the velocity is positive, but the acceleration is negative, just to make this concrete. So we'll say velocity positive, acceleration negative here. If I were to plot the velocity as a function of time here, a positive velocity would just mean that the value is staying above the time axis. A negative acceleration, again, it's the same deal here. The acceleration is the slope of the tangent line of the velocity time graph. So here, if the acceleration were negative, that would mean that my velocity function has a negative slope. Okay, so then what that means is that I'm moving to the right, but I'm slowing down. So if we draw these as with vector arrows, my velocity vector would be pointing to the right, but the acceleration, because it's negative, would be pointing to the left. And that's how we would interpret that. Let's run through another few examples of that just to make this concrete. Let's go and look at a case where the signs are the same. So let's say that, let's do different signs again. Let's say velocity negative, acceleration positive here. Again, we can do the same kind of thing. Boom, boom, v, t. And since we said the velocity was negative, I'm going to have to extend down here. So here, if I were going to plot it, I would have a curve that's doing something like this. The velocity, we can see the velocity is negative because it's below the axis on the velocity time graph. But since the acceleration is positive, that means the slope of the velocity time graph would have to be positive. So since the velocity itself is negative, that means the velocity vector would be pointing to the left. But since the acceleration is positive, that would mean that my acceleration vector is pointing to the right. Now, you might wonder, can they ever have the same signs then? And the answer is sure they can. So let's go and work through those cases. So let's do the case of velocity and acceleration both positive. In fact, why don't you just take a half a second and think about what that curve probably looks like. Okay, so let me go ahead and start to draw it in. So there's my velocity axis, there's my time axis, vt. So because velocity is positive, the curve would have to be above the t-axis, and since the acceleration is positive, it would have to slope upward. So it looks something like that. So does that mean I'm going to the right and I'm picking up speed? So velocity points to the right, and acceleration is also going to the right. So what do we have so far? Velocity is positive and acceleration is negative. Then I'm going to the right, but I'm slowing down. If the velocity is negative and the acceleration is positive, I'm going to the left, but again, I'm slowing down because the value is approaching 0. All right, so let's take a look at the last case. And again, you might want to pause the video for a moment and think about what it would look like. And that last case is going to be if the velocity is negative and the acceleration is negative. All right, here we go. So boom, boom, t-axis, v-axis. So since the velocity is negative, that means that the value of the velocity, that the velocity curve has to be below the t-axis. And since the acceleration is negative, that would mean it would have to slope downward. So it would look, say, something like that. So how would I interpret that? Well, let's see. First off, to get the vectors out of the way, the velocity vector would point to the left, and the acceleration vector here would also point to the left. Now if I look at this, I'm going to the left, but notice how the value is getting away from the t-axis. This means we're getting ever bigger and bigger negative numbers, which means we're speeding up. So if the velocity and acceleration are both negative, that means we're moving to the left and speeding up. So actually, let's kind of recap that for a second. If we look here, the velocity and acceleration are both positive, you're moving to the right and speeding up. If they're both negative, you're moving to the left and speeding up. So if the velocity and acceleration point in the same direction, if they're parallel, that means you're speeding up. If the velocity and the acceleration point in opposite directions, what physicists annoyingly call anti-parallel, and I'll do that too. If they're anti-parallel, that means that they point in exactly the opposite direction. Then you're slowing down. So here you're moving to the right, but since the acceleration is anti-parallel, you're slowing down. Here you're moving to the left, but since the acceleration is anti-parallel, you're slowing down. Moving to the right and the acceleration is parallel, speeding up. Moving to the left and the acceleration is parallel, also speeding up. So the acceleration and velocity can point any which way with respect to each other. But as we're looking at in one dimension, what we'll be doing is telling us whether it's speeding up or slowing down. when we extend this into 2 dimensions and more, then it will also start to tell us additionally how an object might be curving as it's moving through. Okay, so this does give us a few special prototype cases that are worth looking at. Some graphs that are worth kind of committing to memory here are if you have a situation where the velocity is equal to a constant. So constant velocity. In that case, we've already ascertained from the previous video series that the position time graph would be some sort of a straight line, like so. Oops, so that's position, that's time. And then the corresponding velocity time graph, VT, would be, we determined, some sort of flat line, like so. And this is because the velocity at any given time is equal to the slope of the position time graph. If it's uniform motion, the slope never changes, so the value of the velocity never changes. Now we could have this sloping down, and this could be below the curve because it's negative value, but just the key thing here is straight line, horizontal line. And then finally, the slope of our velocity time graph at any given point is equal to the value of the acceleration at that same time. So it would turn out that, let's see here, orange. The acceleration, whoops, sorry about that. There we go. Turn out that the acceleration would be exactly equal to 0. So that's, if you have uniform motion, your graphs are going to look something like that. All right. What's more typical is that you'll have a constant velocity, constant acceleration. And this is because, as we'll see later, the effect of forces being applied to things is to give them an acceleration. So this is why we're going to care. So in the case of, so here let's start with the acceleration and work our way from there. So again, same kind of deal. There will be similar situations to the ones I'm drawing, but just to keep it simple here, let's do a constant, whoops, positive acceleration. All right, so if I do a constant positive acceleration, then the velocity time graph is going to be one that has a constant positive slope. So maybe looking something like that. Now here's the tricky one. What does the position time graph look like? Well, at any instant, the value of the position time graph, and actually just to make things a little easier for me drawing this, let me move this line down to the, no, I should probably leave it. I'll just deal. So what do we get out of these? So what's it going to be for our position time graph? And this is a little tricky because the value of the velocity time graph is constantly increasing. So that means that the slope of the position time graph also has to be constantly increasing. And mathematicians have proven that this shape is actually a parabola. And there's a cute little trick that you can do if you're faced with a position time graph to figure out if the acceleration is positive or negative. If the parabola is like this kind here, where it holds water, so if it looks something like that, this would be holds water, right? Then that is going to mean that the acceleration is positive. And if the curve spills water, then that means that the acceleration will be negative. Alrighty. And let's see, in the next video here, we will go and take a look at the special case of motion under constant acceleration, because it does tend to show up a lot in practical problems. And we will use that to figure out things more quantitatively. So catch you in the next one.